These are your 8.5A notes. We're going to take 3 days on 8.5, and this section is jam-packed with a lot of review information from middle school, but it's necessary information. So I'm going to try to go as fast as I can, but it's important to understand the terminology. So just like any first day, these are a little bit longer than the other sections. So we're first going to talk about factoring, what the heck factoring is. Eventually, we are going to work with factoring polynomials, taking apart polynomials. So the first part of Chapter 8 dealt with putting it together, adding them, subtracting them, multiplying them, foiling them. And so now what we're going to do is we're going to undo all of that stuff and take it back to what was before. So in order to do that, and there's different strategies of factoring depending on what type of polynomial you have, we have to really review what a factor is, what factoring means, what's a prime factorization, what does prime mean, all this terminology. So I'm going to try to go as fast as possible. And then you can go ahead and pause or play back. So I'd just like to start off with what the heck is a factor. And so a factor is a number that divides evenly into another number. Divides evenly into another number. And so divides evenly, just to clarify, means that there is no remainder. If we were to actually do some long division, it wouldn't be a decimal, there wouldn't be any remainder, there wouldn't be any fraction left over. It divides evenly. And two factor, if anything says two factor, it means a number should be written as a product of its factors. So I like to introduce this with numbers because it's something we can wrap our brains around. The factors of 10, well, 1 times 10 are factors of 10. And actually, I should just say 1 and 10. They're both factors of 10 if I'm just listing them. 2 is a factor of 10, which means 5 is a factor of 10 because 2 goes into 10 5 times. And so all of those divide 10 evenly. 1 goes into 10 10 times. 10 goes into 10 once. 2 goes into 10 5 times, and 5 goes into 10 2 times. So those are all the factors. The factors of 5 are just 1 and 5. There are no other numbers that go into 5 evenly. And then the factors of 24, there's several. You have 1, and so it's kind of nice to list the one that goes with 1, 24. 2 goes into 24, so does 12 then. 3 goes into 24, so does 8. 4 goes into 24, and so does 6. And then I've reached all of them because the next number would be 5. I'm counting up, and 5 doesn't go into it. And then I get to 6, and it's already listed. So if you list both factors, you kind of get 2 for 1 there. You don't have to go through the whole list of 24. So the factored form of 10, is really 1 times 10, writing it as a product of its factors, or we could write it as 2 times 5. The factored form of 5 is 1 times 5. It's done. It's really just 5. And in the factored form of 24, I could technically take all of those factors over there and write it as 1 times 24, or 2 times 12, or 3 times 8, or 4 times 6. Those are all factored forms of 24. Because if you look above, it says in the definition, it's writing the number as a product of its factors. So all of those are products, they're multiplication problems, that equal 24 or equal 10. Now there's this thing called prime factorization that actually says, I want you to write it as its factors that don't have any more factors. So for instance, when you look at 1 times 10, 10 has more factors, and so we could actually, technically speaking, this is the best choice, 2 times 5. When we factor 24, all of these could be factored again. 24 can be factored, 12 can be factored, 8 can be factored again, 4 and 6 can be factored again. And so What we like to do is we like to factor all the way down to where you can't factor anymore, and then we don't have to worry about all these multiple answers. Every single one of us would give the same answer. So if I just stick here with 24 just for a second, and I'll give you the formal definition of this later, we do factor trees. So I know you remember factor trees. If I take the number 24 and break it into maybe a 2 times 12 factor tree, this factor can no longer be broke down. It's called a prime number, and I'll define that on the next page. There's no other factors besides itself and 1. 5 is another prime number. It only has itself and 1 as factors. But when I look at 12, I know there's other numbers that I can break that into. Okay, and so I can break it into 4 and 3, or I can break it into 6 and 2. It can be different. But in the end, when I break down the 4 again, I get 2 more 2's. 3 is all the way down to its prime. 2 is all the way down to its prime value, and so is the other 2. So in this factor tree of 24, when I completely factor it, I have 2 times 2 times 2 times 3. So we could write that as 2 cubed times 3. And if you type that into your calculator, you would get 24. So let's look at another factor tree. Maybe somebody else decided, instead of breaking 24 into 2 times 12, they decided to break it into 4 times 6, a different tree. Still the products of 24, both of them can be broken down again, and that's called a composite number. 4 is composite because it can be factored again into 2 and 2, and 6 is composite. It can be factored into 2 and 3. Now I have 2 times 2 times 2 times 3, or again, I have 2 cubed times 3. So my tree looks a little different. The approach, the path getting there looks different, but in the end, we got the same answer as we did in the first tree. We could also do a tree of 3 times 8. So if I were to take 24 and rewrite it as 3 times 8, 3 is already prime. It's already broken down all the way. 8 can be broken into 4 times 2, and 2 is done. And then the 4 can be broken down again into 2 times 2. So once again, we have 2 times 2 times 2 times 3, or 2 cubed times 3. So in every scenario, we get the same answer. So that's why we like to take our numbers down to the prime factor, the prime factorization, so that we're not looking at several different answers. I didn't have to think about it. 2 times 12 broke down to 2 cubed times 3. 3 times 8 broke down to 2 cubed times 3, and so did 4 times 6. So we take numbers down. Not only do we factor them and write them as a factor, as a product, we take them down to the smallest possible numbers. So here are some definitions, and a lot of them should be repeat, and a lot of them I just used on that previous page. So a prime number, any whole number greater than 1, whose only factors are 1 and itself. So an example of that would be 5 on the other page. The only way we could break it down is we could say 1 times 5. The only even prime number is 2. The reason it's the only even prime, any other even number has 2 in it. So they're not prime anymore. Composite numbers are just the opposite of prime numbers. The composite numbers are whole numbers greater than 1 that has more than 2 factors. So all of those other numbers that I listed on the other page, we had 24, we had 10, any of those numbers. Notice we don't talk about 1. 1 is neither prime nor composite. It's part of the definition of those. So 1's just kind of on its own. I mentioned prime factorization, factoring a number down to its primes. That's the name, prime factorization. When a number is expressed as the product of all prime numbers. So on the first page there, when we rewrote 24, we rewrote 24 as 2 cubed times 3. And so it's only prime numbers. 2 cannot be broken down any further, and either can 3. Now we're going to talk about greatest common factor, because this is finding a common number between numbers. So you're comparing a couple numbers, not just looking at 24, but maybe looking at 24 and 10, maybe looking at 24 and 15 and saying, what do they have in common? And it's the greatest common factor because it's the largest one. So you're trying to find the biggest number, which in this case could be numbers and variables that are the same between numbers. So we're going to talk more about that. So let's just practice a few of these concepts before we move on. So let's classify as prime or composite. If it is composite, we want to factor it completely. So 22 is a composite number. I know that because I can see that 2 and 11 go into it. So I'm going to do a factor tree. I'm going to break 22 into 2 and 11, and I realize this is prime and this is prime, so I'm done. So 2 times 11 is the factored form of 22. 13, I can't think of any number that goes into 13, and that's right, because it's prime. The only numbers that go into 13 are 13 and 1, so it's called a prime number. 20, I can think of several offhand. It's even, so I know 2 goes into it. It's composite. And your trees may all look different. You could do a 2 times 10 tree. You could do a 4 times 5 tree. I'm going to do 4 and 5. 5 is prime. I just circle it so I remember it. And then 2 times 2. Sometimes with bigger numbers, we sort of lose one of those values. So by circling it, it kind of sticks out. So the prime factored form of 20 is 2 squared times 5. And you can check your answer by plugging in 2 squared times 5 on your calculator, and you should get 20. All right, moving on. Prime factorization, okay, a little bit more. So these are both, they're telling us that they're composite. So when we factor these, 30, actually I should go back. I gave the prime factorization for 20 and for 22. For 20, if you had 2 squared times 5, that's fine. But because they just said to factor the number, technically 4 times 5 would be okay, and technically 2 times 10. If they say factor completely, then you got to take it down. So any one of those 3 answers works there. So factor completely or prime factorization are basically the same thing. So for number 4, 30, I'm going to break down into 6 and 5. Again, you could break it down into any of the 2 factors, but continue to break down the 6 into 2 and 3. I have 2 times 3 times 5. That is the prime factorization of 30. Number 5, 84, getting a little bit bigger. So I don't know all my multiples of 84, but I see the 8, I see the 4. I know 4 goes into it evenly. So I'm going to start there. And I know 4 goes into it 21 times. I can work with 4. I know 4 can break down to 2 and 2, so I'm done with the 4. And 21 can be broken into 3 and 7, and I'm done. So 2 squared times 3 times 7 is the prime factored form of 84. Now, to write down the prime factorization of variables, you just simply break them down. You can leave it there because x squared is just x times x, and then y times y times y. So just remember that. And also with a negative, you should always take the negative 1 out first. We always just take the negative and put it with the 1. Otherwise, you could get into an argument of, well, I want the 2 to be negative, or I want a 3 to be negative, or a 4 to be negative. Make the negative 1. So our first branch of any negative number is always negative 1 times that number. We'll deal with these variables later. And then 132, I know 4 goes into that, so I'm going to do 4 again, and 4 goes into that 33 times, I believe, is the right answer. I'm guessing. And so 4 times 33 is 132. The 4 becomes 2 times 2, and 33 becomes 3 and 11. So don't forget about negative 1. It was a factor, times 2 times 2 times 3 times 11. Now, some books require that you write it that way. They may require XX, YYY, or some books allow you to do the 2 squared, x squared, y cubed. So you just keep the variables with it. But it's good to understand and remember that x squared is just 2 x's being multiplied together, and y cubed is 3 y's being multiplied together. So next couple problems before we even start the lesson in factoring polynomials, we have to understand this concept of a greatest common factor. So now I'm looking at 2 numbers, and it could be 2 or 3 or 4 or 5. There's no limit. So you're looking for the common factors between these numbers. So the easiest way is to look at their prime factorization. You could list it. A lot of times with numbers you just sort of know, but I'm going to show you with these numbers how to do it in a chart fashion, so when you get into more difficult problems, you can use it as a tool. So I'm going to make a tree for 18. I'm going to break 18 into 6 and 3, and then 6 becomes 2 and 3. And so the prime factorization of 18 is 2 times 3 times 3. And I'll come back to that in just a second. Let's do the same thing with 72. So I'm going to take 72. I know 8 times 9 is 72. 8 becomes 4 times 2. 9 becomes 3 times 3. 4 becomes 2 times 2. So I have 2 times 2 times 2 times 3 times 3. So now what I can do is I can look for all the common ones. The easiest way to see who's in common is you take all of this information and you put it in a chart. So 18 is really the number 2 times 3 times 3. Now what I did is I made little columns. There's a 2 column, there's a 3 column, and there's another 3 column. If it's with the same number, you can't put 2 3's in the same column. So this is 18. It created those columns. Now, if 72 has any numbers that are already where there's a column made, we can plug them in there. So 18 made a 2 column. So one of these 2's from 72 can go in that 2 column. But it has 2 more 2's. So we got to add another 2 column and another 2 column. And then 3 times 3, well, they can share this 3 and they can share this 3. And so when you look at all the things in common between 18 and 72, you can take all the common ones. They have 2 in common, they have 3 in common, and they have another 3 in common. So 2 times 3 times 3 is your greatest common factor. These other 2 numbers over here, they had nothing in common. There wasn't anything in 18. So when you take 2 times 3 times 3, you end up with 18 itself. 18 is the biggest factor between 72 and 18. Don't know if you knew this, but 18 goes into 72 4 times, and 18 goes into itself 1 time. So sometimes a number is the greatest common factor. So that is the easiest way to get the biggest number. I think if you were just to look at those 2 numbers and try to eyeball it, you probably would have said 9. We know that 9 goes into 72 and 9 goes into 18, but it wasn't big enough. So the easiest way is to use that little chart. And you can eyeball it, but with bigger numbers, you might want to stick to the chart. The other time it's a little bit easier until you get good at these is to use the chart when you have variables. So let's look at 2x squared y. So if I take 2x squared y, 2 is pretty easy. It's just 2. X squared I can rewrite as x times x. There's 2 of them, and then y gets a column. So 2x squared y created 4 columns. A column of 2's, x, x, and y. So if 10 has anything to share, we can put them in there. So 10x y squared, well 10, if you think in your head, is 2 times 5. They can share the 2, but they don't share the 5, so 5 needs its own column. They can share a column of x. They can share 1 column of y, but the other y needs its own column. And so when you compare all of these numbers, the greatest common factor is going to be everything they have in common. So they have a 2 in common, so I'm going to bring that down. They have one of these. They have an x in common, and they have a y in common. So it seems like a lot of work, but it is the most accurate, least painful way to get the greatest common factor of 2xy. And you can look at that and you could say, well, I know 2 goes into itself and I know 2 goes into 10. They both have x's, but the 10 only had 1x, so we can't take out more than what we have. And they both have y's, but the 2x squared only had 1y. So you can take an x out and a y out because they both have that many. So as you get better with these, you won't need the chart. I just like to show you the chart so that you have it at your disposal. All right, so let's take all of that concept and we're going to use greatest common factor to break apart polynomials. So what we're going to have is we're going to have something that was distributed, and we want to now undistribute that number. So it's always the first type of factoring when you have a polynomial. These polynomials are just like numbers, so we're going to keep some of that same concept of factoring a number, writing it as a product, all of that stuff we just talked about. So you're going to determine the GCF. You're going to divide each term by the GCF because if we distributed, that's multiplication, we're undoing the distributive property. So the undoing of multiplication is division. And then you rewrite as a product. So all of your answers are going to be a term on the outside times a parentheses. It's a lot easier just to try it than to talk about it. So here we go. We're going to factor completely. I'm not going to use the tables. I'm going to just do the GCF, but if you have an issue, I can talk about those tables. So the biggest number between 25 and 15 is 5. So my GCF for this problem is 5 something. They both have x's. The first term has 2 x's, and the second term only has 1. So you can't take out more than what you have. So the GCF is 5x. So I am going to undo the distribution. 5x was distributed through these two terms. By saying that the greatest common factor is 5x, that was the number that was outside the parentheses before we distributed. So I'm going to divide by 5x, and I'm going to place it on the outside of the parentheses, because that's how you actually divide these things. That's how you undo the distribution. And so now 25 divided by 5 is 5, and an x squared divided by an x is just x. 15 divided by 5 is a positive 3, and the x is simplified to 1. And so what we're left with is a distributive property problem. In the beginning of chapter 8, this is what they'd say to distribute or multiply. We're undoing that. We have a product, and the product equals what the answer was, or the question was in the beginning. Excuse me. All right, 3 more problems. We can do this. So number 8 here, I'm looking at these two terms, 4x and negative 32. Trying to figure out what 4x and 32 have in common. Well, there is no variable in the 32, so there's going to be no variable that they share. 4 goes into 32, and 4 also goes into itself. So my greatest common factor is 4. Once I identify my greatest common factor of 4, I'm going to divide both terms by 4, and then that goes on the outside. This is the biggest mistake, is people divide by 4 and then they get rid of it. Factoring is writing the answer in terms of a product. So you got to have that 4 on the outside. When I divide 4x by 4, I'm left with x. And when I divide a negative 32 by 4, I'm left with a negative 8. And you are factored. You could check your work by actually distributing, and you get 4x squared, or 4x minus 32. And that's exactly what we started with. So that's not your answer. Your answer is the product. Number 9. Number 9, I want to show you a little trick. And I want to make a mistake on purpose. So if you look at this, let's talk about what the GCF is. the greatest common factor between 12 and 16, the number part of the greatest common factor is 4. But let's just pretend that it was 2, that we didn't see the 4. And then between a squared and a, we do realize that it is a. So what if we don't take out the greatest common factor? What if we only take out a common factor? It's going to happen, and I want to show you how to correct your mistake before you start all over. It happens all the time. So we're going to divide both of them by our pretend greatest common factor. It's a common factor, it's just not the largest one. And then from there, I put the 2a on the outside. That leaves me with 6a plus 8. Okay, the a's simplify, and 16 divided by 2 is 8. And now I'm in factored form. But what you should always do when you're in factored form is do a quick little check of your terms. You should always check to make sure that you factored completely, that you have the prime factorization of the number. Okay, and so this is like our tree diagram. If one of the factors could be factored again, we need to do that. And so I see that 6 and 8 also have a 2 in common. What that tells me, we should have taken out more than 2a. But we don't have to start over. We just simply repeat the process, take out the new greatest common factor between those two terms, which is 2, and then it gets multiplied on the outside. So it gets multiplied by the 2a. 2 times 2a ends up giving us our 4a that we should have started with. So even though we did say that the greatest common factor was 2a, we know it's 4a. And so we eventually get there. 6a divided by 2 leaves me with a 3a, and an 8 divided by 2 leaves me with 4. And so this is the true prime factorization of that number. Now, if I were to multiply both of those through, I would get the right answer. I would get 12a squared plus 16a. So the multiplying through to check your answers only checks if you did the math right. You always have to check for more factoring just in case. So when I look at a 3a and I look at a 4, the only thing they have in common with each other is 1. So that means that term is now prime. We have the prime factorization of these numbers. All right, one more. We haven't done any trinomials. Let's just do a quick trinomial. So looking at 9x squared plus 6x minus 3. What I'd like you guys to do today, or on tomorrow's homework, off to the side before you begin, write down your GCF so that I can see quickly what you think the greatest common factor is. So between the numbers 9, 6, and 3, I know the biggest thing that you can take out of all of them is 3. 3 goes into all of them. And we can't take out an x because 3 doesn't have an x. So that's just it. It's just divide by 3. So we're going to divide all 3 of these by 3. That 3 goes on the outside. 3 times something. 9 divided by 3 is 3x squared. 6 divided by 3 is a positive 2 with the x. And a negative 3 divided by 3 leaves us with a negative 1. However many terms we divided up here, they should be the same numbers down here. Many times, this negative 3 divided by 3, people cancel it, and it simplifies to 1. So a lot of times we miss that minus 1 at the end. And that's your factored form. There's no more factoring that can be done. All right, so here's your last part. I want you to tell me what's wrong, why that is not factored correctly, and I need you to factor this problem completely.